Representing motion information, encoding from velocity versus time to acceleration versus time and displacement versus time. So we're going from V versus T to A versus T and D versus T. Lots to do here. All right. Well, the first thing I'd like to show is the fact that we have this formal definition for acceleration right here. And that being the case, we see that acceleration is delta V over delta T, which is V minus V naught over T minus T naught. The graph for velocity versus time now has a change in velocity, which is an acceleration. So you'll notice from 0 to 5 seconds that the velocity increases from a V naught of 0 to a V of 5 meters per second. So the idea here is that this thing is essentially the slope here. So that's the slope. It's another formula for slope, but it pertains to velocity instead of displacement. The change in velocity over change in time, rise over run. And that slope will translate to this graph over here, acceleration versus time in meters per second, or we can say that as meters per second squared. Let's clean up the board a bit. And what I'm going to do is run through a very formal case, run through the definition so you see how it works. It's very similar to how we got velocity from a displacement versus time graph. And so we have V is 5 meters per second minus V naught, which is 0 meters per second, divided by 5 seconds minus 0 seconds. So altogether, that gives us 1 meter per second, or we can write that, like I said before, this is equivalent, and usually you'll see it this way in any textbook like yours, 1 meter per second squared. That means we're gaining 1 meter per second every second, okay? So what we'll do is work with the plot, and over here, at the 1 meter per second squared, we'll put our constant velocity of 1, and we notice that from 5 to 10 seconds, from 5 to 10 seconds, we have a constant velocity, a flat 0 slope. That means the acceleration is 0. Even though the object is moving, it's moving at a constant velocity. There is an area here. We'll get to area next when we look at how far we've traveled. That area indicates that we're moving a certain displacement, okay? So from 15 to 20 seconds, though, we'll realize that we have a special case of the 0 slope, and that's at 0 velocity. So it's flat, and it also indicates that there's no movement. But either way, it'll look the same on the acceleration versus time graph because there's no acceleration. Okay, what's going on from 10 to 15 seconds? Well, let's clean up the board just a little bit. All right, and what we'll have is a negative slope, and it's actually the same slope but negative as the one we started. So it's -1 because we have a rise of -5 and a run of 5, and so we can go back and indicate that the velocity here is going to be, the acceleration here is going to be -1 meters per second squared. All right, we established from 15 to 20 seconds. There is no acceleration. So we're almost done. Now, notice the slope here from 20 seconds to 30 seconds. The slope is the same throughout. So rather than try to look at the 5-second interval, it's much easier to go look at the interval over here that is 10 seconds long, okay? So we'll do just that. It looks like we're going from a rise of -5, so it's -5 meters per second. Meters per second, there we go. Divided by 10 seconds. Over 10 seconds is the time interval. And so we get negative 1/2 or 0.5 meters per second squared. So when we go back over here, what we'll notice is that for this whole interval where we have a negative velocity, we have negative velocity, but we also are gaining speed in the negative direction. So this slope being negative means that we are actually traveling in such a way that we're gaining velocity, but in the negative direction. Okay, so the term deceleration is one that we don't really like because it just indicates slowing down, but we would rather use the term negative acceleration as the way to go. So yes, deceleration is bad. We don't like that. So deceleration is no good. We don't like this. We would call it a negative acceleration instead. Okay? So we'll get rid of all this stuff over here. We'll do erase, erase, erase. Get one layer there erased, and then the next stuff erased. And we're ready to move on to the next piece. We're done with our acceleration versus time graph. Let's go on to fill out the displacement versus time. And so we're back, all cleaned up, and what we have is now a velocity versus time graph, the same one as before, but we want to encode that information and represent it as displacement versus time. And I think this one's going to be a little bit more interesting. The other one dealt with slopes, of course. This one's going to deal with area. All right. So that being the case, the way we approach this is the same as before. We're going to plot points on the displacement versus time graph after determining the areas. And then what we're going to do is connect them together. All right. And when we do that, it's going to look a little more interesting than it had been before due to the fact that we have a changing velocity. We have these accelerations over here. All right. So the first piece is to get the area of this triangle over here. That tells us how far we've traveled in the first 5 seconds. All right. So we know that the area of a triangle is 1/2 base times height, and the base in this case, we have 1/2. The base is 5 seconds, and the height is in meters per second, and that height looks like it's 5 times 5 meters per second, like so. All right, not too bad. That equals 12.5 meters, like so. So I'll put a little dot over here at 12.5 meters. Let's see if I can do that pretty simply. So I'm going to estimate it to be about there. There's our dot. Beautiful. Okay, let's clean up the board a little bit and see what happens. All right, so we're done with those areas for the first 5 seconds. Now, for 5 to 10 seconds, we have a constant velocity, and so we just take the area of this rectangle. So it looks like it's 5 by 5 base times height. 5 meters per second times 5 seconds gives us 25. So it's 25 meters from interval 5 to 10 seconds. And so, that being the case, we want to add that to the previous position over here. All right, if we do that, what does it become? Well, we've got 12.5 and 25, about 37.5, so I'm going to mark that here, like that. All right, once again, we'll clean up our board, and then look at the area over here. It looks like it's at the same size. It's the same sized area as before. 1/2 base times height, the triangle. The height is, again, 5 meters per second. The base is 5 seconds. So we go another 12.5 from 37.5. So it looks like we're at 50. So we had the 12.5, or we were at position 37.5 meters plus another 12.5. So that gives us 50 meters. All right. So we're about here. Okay, so let's mark that off with a dot as well, like so. All right, once again, clean up the board. 15 to 20 seconds, no velocity. What do you think that means? Well, by now we know if we don't move, our position stays the same. So our displacement is exactly the same. So we're going to stay at position 50, dot right there. Now we've got an area over 10 seconds that we can evaluate. We can try to do it over the 5 seconds, but we're really estimating what this value is, right here. So rather than do that, let's just do the area for this entire triangle. And notice that this area right here, that area is negative, which means we'll be going backwards. All right. So we have 1/2 base times height. Okay. The base now is 10 seconds. So I'll get the 1/2. 10 seconds times the height is 5 meters per second. Okay, so it's 5 meters per second, negative, in fact. That's why we're going backwards. So we have negative 50 divided by 2 is negative 25 meters. All right, so we're going backwards 25 meters. Where do we end up? Well, we end up at position 25, so that's about here. So after the 30 seconds, we are right here. Now comes the fun. What we're going to try to do is figure out what the graph looks like in terms of the changing slopes. All right, so over here, from 0 to 5 seconds, we are gaining velocity. So our slope will start gradual, and it will actually pick up and get steeper. So it's going to go like this and whoosh, curve up like that. So it's not a straight line, it actually curves. Here though, we're at constant velocity from 5 to 10 seconds. So we're actually going to go in a straight line like so from there. So I tried to make it kind of straight. There it goes. Next, we have a negative slope. All right, so what's going to happen here is that our velocity is decreasing, so our slope should also get flatter. So we're going to start off a little steep and get a little flatter like that. Over here we're at the same position, so we just connect that right across. All right, and here, check it out, we're actually gaining velocity but in the negative direction. So our slope will get steeper but more negative. Okay, so we start off kind of gradual and then get steeper and steeper like that. So it looks like this, something like that, where the slope gets steeper. So you see in a couple cases over here, we have the slope curved over here. All right, so that's curved. I'll write that down. Curved. Over here, because of the changing velocity, over here it's curved. All right, so curved. And also over here, curved. And the curve depends on the slope. We want to be increasing the slope here. We want to be decreasing the slope here because of the velocity going down. And because we are gaining velocity in the negative direction, that means the slope will increase. Okay, so we get this kind of shape over here. It's something that's more realistic, looks like something we might have seen on DanceStat graph. And so we're finally getting into motion that represents something that is in our everyday lives. All right, so thank you much. And what I'm going to say is Morad out.